This is section 7.4, arc length and surfaces of revolution. All right, so we're going to be working tonight on these two concepts, the arc length of a smooth curve and the area of the surface of the solid of revolution, as we described before when we were finding those volumes. But this will be the surface area of those. So again, we're going to go to that theme of we're going to find something that we do know how to do from pre-calculus and expand that idea to calculus. So we know, of course, that if we have 2 points in space and one is called x sub 1, y sub 1, the other one is called x sub 2, y sub 2. We know how to find the distance between those 2 points, d. Using the distance formula, we know that that is the square root of x sub 2 minus x sub 1 squared plus the quantity y sub 2 minus y sub 1 quantity squared. And what we'll be doing here is estimating the arc length of a curve using those 2 points. And so we're going to estimate the distance along the curve from there to there using that straight length as an estimation of that curved length. So and we will be talking about curves that are rectifiable, which means it has a finite arc length. So for example, I guess we could have something that looks like this, and we find the arc length from, say, this point where x is a to this point where x is b along this function f. So we're going to find the length of the curve, or the length of the arc, along that function f from x equals a to x equals b. Okay? So such a function that will be able to be rectifiable is that its derivative has to be continuous. And since the function is continuously differentiable on the interval from a to b, and its graph on the interval from a to b will be a smooth curve. And we'll be able to find those arc lengths. So turning to figure 7.37, they have a picture of this with looks like a downward pointing parabola, quadratic function, a parabola. And they're just trying to set that up into intervals from x sub naught, which is a, to x sub n. And for each of those subdivisions, from like say x sub 1 to x sub 2, we're going to find the length of the segment from x sub 1, y sub 1 to x sub 2, y sub 2 as an approximation of that curve length. And if you turn to the next pages, I think I copied this for you, and it goes through the process. And I guess I can go through some of this this time. This is not something you're accountable for, so I just wanted to kind of show you how it's done. What we're going to be doing is adding up little bitty distance formula answers from the first subdivision to the nth one, and it will be taking, kind of in a general way, x sub I minus x sub I minus 1, so that's the x before it, squared, plus y sub I minus y sub I minus 1, the y before the ith y, squared. And this x sub I minus x sub I minus 1, that's going to be for us a common delta x. We're not going to make that changing. Technically it could, and it would be a stronger theorem if we allowed for that. But that's okay. We're going to say that x sub I minus 1, that's just delta x. That's being squared. And we'll call the change in y that's changing. So for that ith subinterval, we'll call that y sub I minus 1 delta y sub I. So that's change in y for the ith subdivision. Then what we could do with that, and again, you're not going to be responsible for knowing this, but I did want to at least this time take you through the thought process of how we come up with a definite integral for this. And I noticed in their notes they put a sub I on the x, delta x as well, but we didn't on ours. So as the magnitude of the width goes to 0, that's what they're going to have to require. We're going to be able to say, because our delta x's are all the same size, that means that n is going to infinity is sufficient. Anyway, getting back to this. If I multiplied that second item, that delta y sub I, by a form of 1, which I'm going to use, the form of 1 I want to use is delta x squared over delta x squared. Then there would be a delta x squared that can be factored out of both. So that would leave a 1 from delta x squared because I'm pulling delta x squared out. And I would be left with delta y sub I over delta x squared. And this is the delta x squared that I factored out as a common factor. Then I can split that into two radicals. The radical of the binomial looking thing I have there. Write all that down. And then the square root of delta x squared is delta x. Okay. And of course this approximation gets better and better, as I said earlier, as n goes to infinity. And so the actual arc length, and I used S like they did up here. I'll show you. I call that arc length S, which is a pretty good notation from pre-calculus. I'm going to call that L for length because the symbol that we're going to use for the surface area is going to be S, but a capital S, and sometimes it's hard to tell the difference between a lowercase s when it's handwritten and an uppercase S. So for arc length, let's use capital L, and later on for surface area, we'll use capital S. That'll be the only difference we have from the formulas that the book has. So what we'll find, therefore, is that we'll get the actual length of that arc if we take the limit as n approaches infinity, which we can do that one because we made delta x consistent and always the same, never changing from one to the other. And so this will be from I equals 1 to n of the square root of 1 plus delta y over delta x. I'm sorry, I forgot the subscript. Delta y sub I over delta x squared times delta x. And we know that because of the mean value theorem, and I'll remind you of what that is. Let me draw that over to the side here. The mean value theorem says that for any curve that we have from, say, x equals a to b, where it's a continuous and differentiable curve on that interval, that if we found the slope of the line segment from one point to the other on that curve, the slope of that would be called the slope of the secant line. And of course that's y sub 2 f of b minus y sub 1 f of a over x sub 2, which is b, minus x sub 1, which is a. Regular old slope formula. We're guaranteed by the mean value theorem that at least one place somewhere on this curve, the tangent line to the curve, for some point between a and b at least once, will be a tangent that is parallel to that secant. And so we know that the slope of the tangent line is found using the first derivative, and we're going to call that x value that's between a and b, where this is guaranteed to exist, we're going to call that c. It does not have to be at the midpoint. I know it kind of looks like that there. And we know that that point exists, c, that will give us a parallel tangent line to the secant line. And of course what we know from that statement, parallel, is that those two slopes are the same. And so the mean value theorem conclusion is that there's some number c that exists such that this expression is true at least once for a c value between a and b. That's kind of your mean value theorem statement. So we know that there is some place between the left-hand and right-hand sides of the subinterval where there's going to be, I'm going to write it down here, this is more specific to our problem over here. There's going to be some c in that subinterval, so we'll call that c sub I, such that it's equal to the slope of the little secant line that we established earlier, from the point on the right, x sub I, to the point on the left, x sub I minus 1. Oops, don't need that parenthesis. Okay. And that expression on the right is more simply known as the change in y sub I over delta x sub I technically, but remember we decided we were going to go ahead and let these all be the same width. So I'm just going to call it delta x. The theorem actually uses x sub I, but I think that's okay. So that means that into this I can substitute for the delta y sub I over delta x that's inside that radical. Oops. I can substitute for that with f prime. F prime of c sub I, some x coordinate on the interval from the left-hand side of the subinterval to the right, some number between the left and right, c sub I, is going to make that happen where those are the same. And so that allows us to take this limit as n approaches infinity and create a definite integral. So again, we're getting that theme repeated. The definite integral from a to b of the square root of 1 plus f prime of x squared dx. Or if you like the Leibniz notation version of that better than the prime notation, it doesn't really matter to me which one of these you decide to think through and use, because they are identical. It's just a different notation. Those are your two versions of the arc length formula. One with prime notation, one with Leibniz notation. dy dx. Okay, so that is the arc length from A to B along the curve F. All right, so that's now defined. Similar formulas when the information is given as functions of y instead of functions of x can be easily understood. It would be, the arc length would be from C to D, the integral of 1, or square root of 1 plus g prime of y squared dy, or in Leibniz notation, integral from C to D of the square root of 1 plus dx dy, quantity squared dy. So those are the arc length formulas. All right, so now that we have those formulas, let's see if we can apply them to an example or two. All right, example 2. Find the length of the curve y equals x to the 5th over 6 plus 1 over 10x cubed from x equals 1 to x equals 2. Okay, so I'm going to rewrite this function in a better form for finding its derivative, because that is part of this process. So I'm writing that as 1/6 times x to the 5th plus 1/10 times x to the negative 3rd. And the derivative of that function is a necessary part of our formula for the arc length. So let's find that. dy dx will be 5/6 x to the 4th minus 3/10 x to the negative 4th. All right, so looks like we're ready to go into our formula. So the arc length will be the integral from 1 to 2 of the square root of 1 plus the derivative answer we just found squared dx. All right, and I do want to solve this one without a calculator. So buckle up. This is not trivial. Okay, so my first inclination is to see if simplifying that squaring first actually helps me in any way. So I'm going to square that binomial, which gives me the square of the first term, 25 over 36, x to the 4th squared is x to the 8th, minus 2 times 5/6 x to the 4th times 3/10 x to the negative 4th, which is going to simplify to be negative 1/2, plus the second term, 3/10 x to the negative 4th quantity squared, which is 9/100 x to the negative 8 dx. All right. Now collecting like terms, I get 25/36 x to the 8th plus 1/2 plus 9/100 x to the negative 8 dx. My hope is that that trinomial under the radical factors, so I'm going to check to see if it's a trinomial square. If you'll recall from college algebra, you'll know a trinomial square is there when the first term is a perfect square, which it is, the last term is a perfect square, and it is, and if the square root of the first thing, and I always write it down just in case it's going to work, the square root of the first thing, 5/6 x to the 4th, times 2 times the square root of the second term equals the middle term. Let me write down the square root of that second term, 3/10 x to the negative 4th. If the product of those two square roots times 2 equals the middle term 1/2, then we're good to go. And it does. And therefore, whatever the sign of the middle term is, plus in this case, I'll put a plus sign in my binomial, and that's squared. And that's very good, because that means that the square root of that perfect square gives us back the number or the binomial that is squared. All right, so this is now looking quite doable, right? You agree? Okay, so the antiderivative of 5/6 x to the 4th, I'm going to raise the power by 1 to become x to the 5th and divide by the new power, 5, so that'll become 1/6 x to the 5th. And then raising the power by 1 to negative 3. Dividing by that new power will make this negative 1/10 x to the negative 3rd, evaluated from 1 to 2. Okay. And then using the fundamental theorem of calculus, we'll substitute into our antiderivative the upper bound first for each x minus the lower bound substituted into the antiderivative function. And then doing all that arithmetic, you should get 1,261 over 240. All right, so there we go. Nice full example. Now I will tell you that a lot of times these problems, if they're going to work out that way to be pretty and have the square root of something squared, the original function is probably going to have to be as nasty looking as this original one was. That x to the 5th over 6 plus 1 over 10x cubed. That doesn't happen that often that it just perfectly works out. So you may have something like that, but I'll tell you that a lot of these problems will be set up the integral, which at the first line where I wrote L equals, that was the setup. And if that's all I ask you to do is to set up the integral, then you're done. Then I might ask you to go further and use your calculator to find a decimal approximation of that and not have to go through the whole algebraic and antiderivative process like we just did. So sometimes you won't have to do all of that algebra and anti-differentiation that we just went through. But sometimes you will, so just be prepared for either eventuality. Okay, so on to the area of the surface of revolution. So if we revolve a curve about an axis of revolution, let's make it look kind of easy here to start with. If this is our curve, and let's say we're revolving about the x-axis, that's the simplest situation. And we're going to go on this curve from x equals a to x equals b. So that's the portion that's going to be revolved. And as we revolve that part of the curve around, the region between it and the x-axis is revolved, creating a solid, of course. That's what we already talked about. But now we're just revolving the curve itself, which creates the outer surface of that same solid. And so, again, we'll have a representative, whoops, let me do this in a different color to make it clear, not this color. A representative rectangle that's revolved around will create a solid that has a really interesting look to it. And so I think it's on the next page. I have a picture of this, yeah. When that's revolved around, well, actually, the simple version of that, let's start with that first. If I took a line segment from this point on the curve to this point on the curve, from the left side to the right side of that subinterval, then that one line segment, when revolved around your axis of revolution, will look like this. Very poorly drawn. It's supposed to kind of look like a lampshade. Ignore that little line in the middle. I messed up. And if you look at the picture, that's a lot easier to see. And so the length of that line segment we'll call L. And the picture of this lampshade shape that's created, that's called a, oh, it just went out of my head. That'll come back to me later. Anyway, the name of that shape is not the most important part of this, but it is supposedly for us a simple figure. It's called a frustum. Frustrating how I forget that sometimes. It's called a frustum. And the surface area of a frustum is a formula that is supposedly fairly simple. And I better change color, you won't be able to see. And the frustum has two different radii. Let's call this one R2 and call this one R1. Radius at one end versus the radius at the other end. Oops, I meant to call that R1. And I wrote R2 again. R1. There we go. And this formula is S equals 2 pi r. That should sound familiar because that's the circumference, right? And so it's that circumference of a circle multiplied by L. And the r that's in that formula is the average of the two radii of the frustum. And you're not going to need to know this formula and how that's developed. But I do want you to pay attention to that 2 pi r times the length of the segment. because you're going to see how once we write down the formula for the surface area of the solid of revolution, you're going to notice how much we're borrowing from the last formula we just did. And so figure 7.43 has a pretty nice picture. So you can kind of see that little golden frustum kind of looking thing being one subinterval that's been revolved around, creating the frustum shape. And that's pretty close to the surface area shape of the curve that's been revolved, creating that solid. And if you really want to read through all of the explanation, and I misspelled frustum, sometimes I do that. I just realized I did. That's frustrating too. Well, you know what? That could be misspelled. Nope, I think it's right. Frustum is the correct spelling. That will not be tested, so don't worry about it. Anyway, you can read through the development of the formula, and if you want to, and it ends up being this. Without any further ado, here we go. The surface area is 2 pi, go figure, times the integral from a to b of something that's measuring the radius of the frustum. That may be it because I'm mispronouncing it. Could be why I misspell it. Times the length. And this is the part you're supposed to be going, I've seen that before. That's square root of 1 plus the derivative of f quantity squared dx. So really, this looks a whole lot like any of the previous formulas with an extra 2 pi outside and an extra times r of x inside. Or it could be as you'll see in a second, could be a radius in terms of y. If our information is given in the form of x equals f of y. So this would be a radius in terms of y. And of course, a person could use the, well, I guess I can't talk and write at the same time, can use the Leibniz notation version of these derivatives if they prefer. In fact, that's what I generally do. But these are the formulas for the surface area. And we need to explain that radius function in just a second. All right, so the important thing here in getting that radius, that's actually the hardest part of this once you get the formula memorized, is understanding where that's coming from. So let's say that you have a function where y is a function of x. So we're talking about the first situation, which happens more frequently than the other. Let's say that you have a axis of revolution that's not the axis. It could be the axis, a lot of times it is, but let's just say it's at y equals negative k. Not that that matters, but it's not that big of a deal. The radius, if this is the axis of revolution, the radius is going to be the distance from that axis of revolution to the curve. That's your r of x that you're going to have to find. Now, if the axis of revolution happens to be the x-axis itself, then it's just f of x. The distance from the x-axis to that curve is f of x. But in this more general case, it's going to be f of x minus negative k. top minus bottom. Okay, so that's what your radius will be as a function of x. Now, on the other hand, if you're talking about the case where our function looks, let's say, like this, where x is a function g of y, and your axis of revolution, let's say, is x equals k, then the radius is going to be the distance from the axis of revolution to that curve. Now, if that's the y-axis you're revolving around, of course, then that's just x, which is the g of y. That's probably one of the more common ways that's done. Oh, and I forgot to mention the other possibility with the f of x. I just noticed that. Let me go back. I know I'm kind of stopping midstream, but this is an important thing. If over here, just to make this hopefully not very confusing, if my axis of revolution, however, is vertical line, like at x equals, let's say, negative j, then our radius will be from that axis of revolution to the curve. And of course, this part of it from the y-axis over is x. And so the radius in that case, this radius function, will be x, which is g, will be the x value right minus left minus negative j will be plus j. Okay. And if that radius function is a binomial, as I've presented in both of these examples so far, then that would need to be protected inside the integral with parentheses surrounding that binomial in front of the radical. And of course, if it's just the y-axis, then that becomes just plain x plus 0, I guess. So coming back over here, I'm sorry, I'm kind of skipping around a bit here, but so this, the part from the y-axis to the curve is x, and so our radius in this case will be g of, oh, sorry, not radius in terms of x. This is supposed to be in terms of y. That's the situation we're under, sorry. That radius as a function of y will be x, which is g of y, right, minus left, and since so it would be minus k. Or if the axis of revolution were a horizontal line at, let's say, y equals negative j, is our axis of revolution. I forgot to indicate on this one that this is the axis of revolution there. Then we'll be measuring from the axis of revolution to the point on the curve. That should be straight. And that's our radius, which will be, this part of it is y. So if you're revolving about the x-axis, it's just going to be y. But this would be y top minus negative j, so y plus j would be our radius function. So that's the most complicated part of this. And if you need more explanation in class, I'm happy to go over that again or some more with specific examples to help you understand. All right, so I'm going to move to the next example. And you can see the formulas that are given. I wrote most of them. I didn't write the Leibniz notation ones down, but they're pretty easy to get. So, example 3 says, find the area of the surface formed by revolving the graph of f of x equals x cubed on the interval from 0 to 1 about the x-axis. And you're going to like the ones that are about an axis because those are so much easier than the others. Okay, so let's graph this. So y equals x cubed from 0 to 1. That's all we have to really look at because we know the graph comes up like this. Goes like this. And I drew the right side a lot better than I did the left side, but that's okay. So from 0 to 1, that's what we're going to take and revolve that part from here to there about the x-axis. Okay. So our radius is always measured from the axis of revolution to the curve. And obviously that's a measure of y. Since our function is a function of x, and we're not going to use y, we're going to use the f of x, meaning we're going to replace that with x cubed. That's our radius function, okay? Then, of course, for the continuation of our formula, it's going to be a lot like when we did the arc length. We're going to need to know that derivative function of f, so that's 3x squared. And so our arc length will be 2 pi times the radius function, x cubed, times that arc length formula, 1 plus, under the radical, 1 plus our first derivative answer, quantity squared, dx. Okay? And so that is from 0 to 1. I'll leave this one to you to practice doing the anti-differentiation. And if you run into trouble, this would be a good question to ask in class. You should get, when you've practiced this one and gotten all the way to the end, you should get pi over 27 times 10 square roots of 10 minus 1. So that's a good check for you with your Calculus 1 review to make sure that you can get all the way to the end of that answer. All right, so I will see you in class. Until then.